Right, we are now in this section 5. So we have the 5 section. So we are now in the last part of this chapter. We are page 37, and let's go directly into the properties of Laplace transform. There are many properties, and we will take some time to prove them. Let's go through the properties of Laplace transform. Linearity. The Laplace transform of the sum of two time signal f of t and f2 of t that is scaled by some constant can be broken down into individual Laplace transform, implying that we can actually do it this way. The Laplace transform of a f1 t is equals to a Laplace transform of f1 t is equals to AFS, F1S. And similarly, the other one is Laplace transform of A2 F2t is equals to A2 Laplace transform of F2 of t equals to A2 F2 of S. And individually, when they can be summed together such that this happens. Right, so these are linearity property, and it's a very big deal. We also say that the Laplace transform is a linear operator. Okay, so next we have the time derivative properties. We'll go through some of them, and this is the big idea of time derivative. Laplace transform of the differentiation function of a function is simply SFS minus some initial condition, where this is the function itself, and we insert time to be 0, the initial value condition. So we convert a differentiation or differential equation into an algebraic one. So that's the cool idea. That's the first differentiation. If we have n order differentiation, then we have this expression over here. So let's try Laplace transform of d2 f of t dt square is equals to s2 of f of s minus s of small f0 minus f prime of 0. Okay, we're not very pedantic whether it's 0 plus and things like that. We just, it'll be clear from the question given to you. Okay, so this is the expression for the second, the Laplace transform of a second order differential expression. Now we have the integration. The integration is the Laplace transform of this expression is simply fs divided by s. So integration becomes like 1 over s. Notice that this equation is actually ft, right? By the fundamental theorem of calculus, ft is equals to integral of 0 or some a to the t f tau d tau. So this is the fundamental theorem of calculus. It converts a definite integral into an expression. I made a mistake. It should be capital F of t, where the differentiation of capital F of t is equals to f of t. I pull out Wikipedia. The thing I'm pulling out is called the fundamental theorem of calculus. In the first part, it gives you this expression. Capital F of x is the integration of a to the x f of t dt, where this x will be replaced into the small t here to give you capital F of x. So what is f of x? F of x is simply the antiderivative of f of t, or should I say, the derivative of f of x is equal to f of t. This is the fundamental theorem of calculus. So you can pull it out and see it here. So in the Laplace domain, what you will realize is that this integration will produce the antiderivative. The antiderivative is simply represented as 1 over s. The integration of f of s is the antiderivative. So it's a very nice thing that the Laplace domain does for us. Alright, I won't talk about the rest of the table. In this course, we assume that you can copy down this table in your cheat sheet and use it when necessary. Okay, things we will always use is the convolution, the time transformation, the final value and initial value, the complex shifting, the real shifting, integration, and order and linearity. So in fact, almost all. Okay, so just remember to copy down all this and use them in your cheat sheet. So with that, we are going to go through some of the property and derive them in the next few slides.